Hi guys, we're going to talk about section 2.1 here. There's quite a few ideas. I have done this over 2 days in the past. We're going to try to get through it all today, and if we need to have a little work day later, we will. But please pay attention and take some good notes for me. Okay, so basically we're talking about functions and this idea of increasing and decreasing. So the big things that you need to know is that we read a graph just like you read a book. We read left to right, so don't forget this. We read it left to right. And when you're going left to right, if it's going uphill, we call that increasing. If it's going downhill, we call that decreasing, just kind of like positive and negative slope, but we're not just talking about lines. And then if the y stays the same, then we call that constant. Okay, so basically we're going to be looking at some graphs like this, and we're going to say, where are they increasing and where are they decreasing and where are they constant? Now, at the points where they switch, because this one would be like increasing, and then it would be decreasing, and then it would be increasing again. At the points where they switch, we say they're neither increasing or decreasing. So we're going to be using parentheses for everything we talk about with increasing and decreasing. Okay, so here is a fancy definition. It says that a function is increasing if in an interval from a to b, f of a is smaller than f of b. They're saying if the y value on the left is lower than the y value on the right, that means that it's going up. But we can just think of it as uphill. Another definition then would be of decreasing. If f of a is bigger than f of b as you go left to right, then that means f of b y value is smaller, and that's what's making it go downhill. But you can just think of it as downhill. And then the constant would say that f of a equals f of b, and there would be no change in the y value, which is why it's constant. So here's our practice. We're going to figure out the intervals where it is increasing, decreasing, and constant. Now, when I do this, I like to write it on paper and then take it to the math lab. But some of you will go straight to the math lab. That's fine, but this is how I make the fewest mistakes. So I say to myself, what is the graph doing first? Well, the first thing it's doing is decreasing. When is it decreasing? Well, it starts off decreasing. So all the way to the left, it's decreasing. So we say it starts at negative infinity. And then when does it stop decreasing? Well, if I drew a line, the line I would draw to cut it would be right there. And we're talking about x values because we're reading left to right. And it decreases all the way to -1. And it's not decreasing anymore. After that, it starts to be constant. So it's constant from where I left off at -1. And it's constant all the way to this line where I could draw at 3. Then what happens? Then my graph is increasing again. Well, for the first time actually. And it's increasing from the point 3 to where does it stop increasing? To 5. And then it begins decreasing again. So it's decreasing at 5 for the rest of the time. So you have to put a union here to say it's going to decrease again from 5 to infinity. So your math lab would have you write in these values. It's kind of hard to find the decreasing because of the skip. So that's why I kind of like to go in order so I don't miss anything. So what is a relative maximum or a relative minimum? For example, this graph here, it does not have a max or a minimum because it goes up forever and down forever. So there's no, and that's what we call an absolute max or an absolute min. But it does have a relative max or min. A relative max is a maximum in an area. So it's a max in an area. That's what it means, kind of relative. And the same thing with relative min. So if it's its maximum value in its area, we call it a relative max. So this point here would be a relative max because in that area it's a max. This point here would be a relative min because it's a minimum in the area. Other ways you can think of it is as a turning point. If your graph is ever turning from increasing to decreasing, that will be a relative max or a relative min. So we will find those points with our calculators. A lot of time you can put second calculate max or second calculate min, and you can find those values. And those turning points are really important because they tell us where our graph goes from increasing to decreasing. So here's an example. This is a fancy graph. So this one actually does have what we call an absolute minimum. This graph does bottom out right here at this point, but it goes up forever. So there's no absolute maximum. But there is two relative minimums because they both are turning points and one relative maximum. So this guy is also called an absolute minimum. And like I said, they're turning points. It goes from decreasing to increasing right at that point. It goes from increasing to decreasing right at that point. And it goes from decreasing to increasing right at that point. So those turning points tell you where the relative max and minimum are. So here's the calculator problem we're talking about. And it's going to ask us to use our graphing calculator to find the relative max and minimum and to determine where it's increasing or decreasing. So what you're going to do is you're going to type it into your calculator. There's a lot of decimals here. I'm going to write it down here so I can get to it in a minute. 0.1x cubed minus 0.6x squared minus 0.1x plus 2. Okay, so let's see if I can type this in. Okay, 0.1 x to the third. There's a little caret button for me. Oh, too many. What's happening? All right, minus 0.6x squared minus 0.1x plus 2. So when I hit graph, I can see that it's a cubic function. Kind of looks like a little snaker, okay? So they want to know where is the relative max and min. And they also want to know where it's increasing and decreasing. So here's what we're going to do. We're going to find this first point, which that relative max is going to be right around here. So what we're going to do is we're going to hit second calculate. Second trace is a calculate, and you're looking for a maximum value. So that is 4. Now your calculator down here asks you for a left bound because your calculator is stupid. You need to tell it, hey, stupid, where do you want me to start looking? Because it would look forever and graphs will go forever, so it never know when to stop. So you go to the left of where you're looking and you hit enter. And my graph drops a line here. Some of you guys will just have this little arrow saying, I'm going to start looking here. Then it asks you for a right bound. So you hit the right arrow until you're on the right side of it. It doesn't matter where, anywhere really. And then you could say, stop looking here. If you look in between here, I want to know what the maximum value is. It asks you for a guess. The guess is not really necessary unless there were 2 in your region, but I'll hit enter for my guess. And it says that my maximum value is negative 0.08. And this is pretty close to 2. Now your math lab, when it's talking about a max or min, it's talking about a y value. So they want the y value of 2 probably. What is the relative min? Well, that would be in this area. So once again, you're going to do second calculate. Actually, I'm going to write down what this point is so that because I'm going to need it in a minute. So that point is about negative 0.082. Now we'll find the next one. Second, calculate. This time I'm looking for a minimum 3. This is the one I'm looking for, so ask for the left bound. I could technically hit enter right now if I wanted to. Say start looking here. Hit the right arrow, tell it when you want it to stop looking. It can stop looking here. It will be in between. I want to find that spot in between. It asks you to guess. So you move your cursor close to where it is. You hit enter, and there is my minimum value. Again, they want the y value for minimum. It looks like negative 1.6. And that's what they're looking for. But this point is about what? 4.08, negative 1.6. So let's talk about the increasing and decreasing. Well, what is my graph doing first? Well, my graph is first increasing. So when's it increasing? From negative infinity until my turning point, which I could cut right about here. What is the x value? Because you read left to right, this is going back to the x values again, negative 0.08. Then my graph begins to decrease from negative 0.08 to the next turning point, which happened at 4.08. And then it started increasing again. So you would do a union 4.808 to infinity. So that's how you can do the increasing and decreasing. Okay, now we're going to talk about some word problems. Two nurses, Kiara and Matthias, drive away from a hospital at right angles to each other. And Kiara's speed is 35 miles per hour and Matthias is 40 miles per hour. They want to know how far apart they are. Well, that's going to depend on how long they've been driving. So they want us to write an equation for d of t. And they also want us to find the domain of t. The domain of the function is what you plug in for x, or in this case, t. So you can do the domain right now. Then there's two types of people. Some people might say that it's 0 to infinity because time has to be positive. Some people might say, well, it can't be 0 because then they would be on top of each other, and that'd be okay too. If you wanted to say 0 to infinity. Some people might say you can't drive forever. You have to end at some point, and I would accept that argument as well. But they give us a nice little picture of what this would look like. And if you see, if Matisse is going this way, he's going 40 miles for every hour that he goes, and she's going 35 for every mile that she goes. The distance they are apart is that hypotenuse, which is where this equation is coming from. You do not have to solve it for, you could do a square root. D of t equals, if you square root both sides, a gigantic square root of 35t squared plus 40t squared. And you're going to ask me, can't I just simplify those? No, you cannot simplify a square when there's a plus sign inside of it. This is just as simple as it gets, and that could be a function to say how far apart they are. Another function that we can model with here is talking about a storage area. Jenna's restaurant supply, she has 20 feet of dividers, and she has to make this rectangular area, but she's going to use the corner. So like if you use the corner, then you only have to use like 2 walls instead of 4. If the corner is used for storage, she will need 2 rectangles. How can she do this? The area. Well, the area is base times height. So they're going to want us to multiply the 2 sides to get the area that they're talking about. But we don't even know how she's using it. All I know is that there's 20 feet total. So if we don't know how much she's using here, she's using the rest on this side, which would be 20 minus x. And then the area would be the area of the function, 20 times 20 minus x. They also want us to graph it and find the dimensions that will make that a maximum, so they want us to look at the maximum. What is the domain? Well, what can I plug in for x? Well, I can't really plug in 0 because then I don't have a rectangle, but I can get really close to 0 and I can go all the way to 20 because that's all the partition I have. That's the domain. This would be the area, and now we're going to graph it and find the maximum area. We're going to use our calculator, so it's going to be 20 times 20 minus x. You can distribute if you want, or you can just leave it like this. When I graph it, what am I going to be looking at? Well, I don't see anything. Well, why don't I see anything? Well, because I'm talking about distances in the 20s. I bet it's off my chart a little bit here. So what you can do, you can zoom out if you want. I like to use, there's a zoom fit button that works for me a lot. It kind of finds a lot of the action. Zoom 0 helps. Okay, that doesn't give me what I want to see though. Did I type it in right? No, I did not. It was x times 20 minus x. Now let's go back to my graph. It might have been there to begin with. Let's go zoom 6. Yeah, I only saw part of it. I needed to see more of it. So if I go to zoom 0, like I said, zoom fit, you can kind of see more. So now I can go to my window and say, instead of going to -10, let's go all the way over to 25. Let's see what that graph does. And there's where that maximum happens. So I want to know what the maximum value is. So I will do second, calculate maximum, which is 4. I'm going to hit enter here and come over here and find this maximum. And the maximum is going to be at 10 because when 10 is x, the area is going to be 100 and that's going to be a maximum. And I want you to look back at the picture and see if you can understand what that means. Here's their picture. If this is 10, then this would be 20 minus 10, which is 10, which would be a square. And the square is what would maximize the area. So the dimensions would be a 10 foot by 10 foot area. The square would be maximum area. Okay, we're going to talk now about piecewise functions. Piecewise functions are when you have really kind of weirdo graphs and you put them all together. So maybe you have a line and a constant and then a parabola, or a parabola and then a line and then another parabola, these weirdo graphs. So the way we write it is we say this is the whole function is these 3 weirdo pieces. And what happens is this is the rule and this is when you use it, the domain. So when we were talking about those fancy function machines, this one is super fancy. It like has 3 pipes in it almost. So when you plug your value in to this machine, it has these 3 areas the machine is broke up into. And depending on what you plug in is what the machine does. So what this is saying is, so if you plug in a number less than -2, like -10, and you plug it in, that is when it uses this rule, which is -10 plus 1, which is -9. But if you plug in a number in the middle of -2 and 3, like you plug in 0, this machine just shoots out 5s. And if you plug in a number bigger than 3, like 7, it will go into this part of the machine and do what it needs to do. So when they're asking you to find all these values, they're saying f of -5. That means x is -5. What is the machine going to do? Well, where is -5? -5 is less than -2, so it's going to take -5 plus 1, and it will give me -4. When I do f of -3, where does that fit in? That would also be in this first region, which would be -3 plus 1, which is -2. When I plug in 0, f of 0 is in this middle rule now, and the machine just shoots out 5s. If you plug in 3, that's tricky. Which one do I use? Well, this one has the equal sign for 3, and this one does not. That's where it splits. So f of 3 is still using that middle rule, and it will shoot out 5. F of 4 is bigger than 3, so it will take 4 squared, and that will be 16. And f of 10 is definitely bigger than 3. It'll be 10 squared, which is 100. So all you have to do is find the right area, the right domain for your values to figure out what your function will do. They want us to graph this. You will only have to be able to recognize graphs. You will not have to do it by hand. But the way we graph these is you use your brain first. So first look at this and say, what am I dealing with? Well, this is a line. It's kind of flat and it's a positive slope. This guy is a negative slope And if it's multiple choice, that might be enough to get you the right answer. But what we do know for sure is the graph is breaking at 3. This is the breaking point. You don't put a dash here, but sometimes it helps you graph it. So what I like to do is I like to make an XYT table. I'd like to pick some values in here. I know it's going to be a line. I really only need to pick 2 values, and I can graph that piece in that area. And then at the end, I can just erase my dots. So let's pick 0. 0 is less than 3. What's 1/3 times 0? 0. 0 plus 3 is 3. So 0, 3 is on that line. Let's plug in. I can't plug in 3, even though that will be my boundary. So I could plug in 3, but I could put an open circle there. 1/3 of 3 is 1. 1 plus 3 is 4, but it's not going to be on that line. That one gets the open circle. You could go the other route too. I could have plugged in -3 and got -1. -1 plus 3 is 2. And there's that line I was looking for. Now I'm looking for a negative slope line, and I'm picking values greater than equal to 3. So if I pick 3, I get -3 as my answer. And this one does get the solid dot. If I pick 4, I get -4 as my answer. And there goes that line. If I pick 5, I'll get -5. This one is going down. That is my piecewise function. One more practice here. Let's get rid of that. Again, you will just be able to find them on your graphing, your multiple choice. So what I got here, I got a flat line. This is going to be a frowny faced parabola, and this is going to be a positive slope line. So when you're looking for a graph, you're looking for a flat line, a frowning parabola, and then an uphill line. But we're going to make the graphs with our t-table. So it's going to cut up at 0, and it's going to cut up again at 2, and then at the end. Okay, so in this region, I'm going to graph the y equals 4. That is very easy to graph. It's just a flat line. It can equal 0, so all of this will be my first line. Now is the tricky one, okay? So let's plug in 0. Make my XY table here. This gets an open circle, but what's 4 minus 0 squared? That's just 4. And there's already a dot here, so I don't have to do an open because it's already close. If I plug in 1, I'm going to get 4 minus 1 squared, which is 3. And if I plug in 2, I'm going to get an open circle again. I get 4 minus 2 squared, which is 4 minus 4, which is 0. And that one gets the open circle. And it's going to be that frowny parabola like we talked about, so kind of like that. And now for my last point, my XYT table, I'm going to plug in 2, but it will be an open circle. 2 times 2 minus 6, that's 4 minus 6, which is -2. So 2, -2. I'm going to kind of erase these dots because those aren't really part of my graph, remember, just to help me. 2, -2 gets an open circle. This one got the solid circle here, didn't it? I didn't do that right. 2, plug that in. Okay, 2, -2. Let's plug in another number bigger, 3. 2 times 3 is 6. 6 minus 6 is 0. There's that uphill line. And then the slope is 2. Rise 2, run 1. I can do it one more time. There's my piecewise function. Okay, what about this one? This one looks really hard. This one's going to have a hole in it. We haven't really talked about holes. We're going to skip this one and see if it shows up hard on your homework. You probably will want to see me for some homework questions if these get confusing. And the last thing is this greatest integer function. And the symbols are a little bit messed up. It's more like this. And basically what the greatest integer function does is it rounds down. It's a round down function. Some people call it a stair step function. So when you make an XYT table, you want to pick values that are in between, because what happens is 0 rounds down to 0, yes. 1 rounds down to 1, 2 runs down to 2. Those endpoints are on there. But if you pick 1.5, it's going to round down to 1. So it's 1.5 up 1. So you have these stairs. And then once you get to 2, it jumps to the next stair. If I plug in 0.5 into my round down, it rounds down to 0. So the 0.50 is on my graph, 0.60, all those. And you get these little stair step functions. They kind of look like this. Okay, so that is the greatest integer function. You do have some math lab to do, and like I said, I think there might be some homework questions, but we will have time to address those.